Alright, what's up guys? In this video, we're going to pick up with some vector calculus. We're going to be talking about Gauss's divergence theorem here, and talking about outward flux. So we're asked to basically consider the outward flux of the vector field F, which we have here. It's going to be yi plus xyj plus zk, and it's going to be across the surfaces that are enclosed by this cylinder here, which is x squared plus y squared is equal to 4. Z is equal to 4, and the plane Z is equal to 0. And then they give us the cone, which is Z is equal to the square root of x squared plus y squared. They want us to calculate the three-dimensional divergence, and then they want us to use the divergence theorem, also known as Gauss's divergence theorem, to evaluate the flux of the vector field across the surfaces that we were given. And that's basically what we're doing. So what I went ahead and did before the video was sketch the figure. And the reason, or the figure or whatever it is, depending on the circumstances. And the reason why I always go ahead and sketch it first is because sometimes doing the sketching can take a bit of time depending on what it is. This is a cylinder and a cone, so it did take me a little bit of time to get it sketched out. So I went ahead and took care of the sketching beforehand. So, because I'm not that great of a sketcher, but we did need to sketch in this case. And so as you can see here, I have the cylinder, I have the cone here within there. And we're going to use the divergence theorem after to calculate the, to evaluate the flux, that is. And so we're going to do all that on another sheet. So let me first remind you of the divergence theorem and what that is. So let's start off by talking a little bit about that. So the divergence theorem, also known as Gauss's divergence theorem. So divergence theorem. For those of you physics heads out there like myself, I have a physics degree. You probably have seen Gauss's divergence theorem quite a bit. And so remember, it just allows us to relate a surface integral to a volume integral or a triple integral. And remember, it's just the surface integral. S is the surface, and it's going to be f dot n ds. Now remember that n is just the outward unit normal vector to the surface S, and it's going to be equal to the triple integral, or the volume integral, some people call it. And then we're going to have our three-dimensional divergence, which is the dot product of the del operator in the vector field, and that is the divergence theorem. Okay, so hopefully that makes sense. Okay, so given the cone, which was Z is equal to the square root of x squared plus y squared, the plane was Z is equal to 0, comma, Z is equal to 4. Okay, so if we look at Z is equal to the square root of x squared plus y squared, well, we know that 2 squared is 4, and if we wanted to get the x squared plus y squared, we would square that square root. And so if we go back to our cylinder, which was x squared plus y squared is equal to 4, pretty much all we really need to do here is to take our vector field, which we were given up there at the beginning, and we need to go ahead and calculate the three-dimensional divergence, and that's just the dot product of this del operator in that vector field. And remember, it's just going to be our first order continuous partial derivatives, basically. And so that's the first thing that we'll kind of go ahead and do. So we got the three-dimensional divergence. And let me just remind you of the formula for it again. So remember, it's just going to be div. We got our dot product. And it's just the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. Okay. So let's go ahead and calculate our divergence here. So let's look at our vector field. And since it's on another sheet, let me just quickly write down what it is. The sketch itself that I had to sketch took a minute, so it took up the whole paper because I was trying to be as neat with it as I could when I was sketching it. So I kind of ran out of room on the first page. Okay, so that's our vector field. So we just take the components of the vector field, take the partial derivatives, and see what happens. Okay, so we'll get div. That's another way to write it, by the way. All right, so let's go ahead and do this. So looks like we'll have the partial with respect to x, and we got y here. And then we'll add that to the partial with respect to y for xy. And then the partial with respect to z for obviously z. And hopefully you see here that for our three-dimensional divergence here, hopefully you see that we're just going to end up getting x plus 1. Because since we're taking the partial here with respect to x, we're treating y as a constant. So that's just 0, because we know the derivative of any constant is 0. And then here, we're taking the partial with respect to y for xy, so we're treating x as a constant. And so therefore, we just get 1. And then obviously if we're treating y as a constant, or x as a constant, excuse me, and then we just get x, so 1 times x, excuse me, and then we take the partial with respect to z for z, and that's just 1, and that's basically how it goes. And so that's going to be our three-dimensional divergence. Now, to calculate the flux, all we have to do is just use the divergence theorem for that. The problem is, however, we want to try to calculate the triple integral here, or the volume integral. Some people say triple integral, some people say volume integral. But we need to convert it to cylindrical coordinates. Now remember that cylindrical coordinates are really nothing more than polar coordinates extended to three-dimensional space, or polar coordinates in 3 dimensions, basically. So if we go and we look at what we have, oh, and by the way, for cylindrical coordinates, and you will have at least once you get up to this point, have seen most of this before, so it won't be too daunting when you see it. So remember, for the cylindrical coordinates, it's going to be x is equal to r cosine theta, y is equal to r sine theta, and then z is equal to z. Okay, it's just, again, we know for our polar coordinates, x is equal to r cosine theta, y is equal to r sine theta. Again, it's just an extension of those polar coordinates over 3-dimensional space. And remember that the dv part that you see in our formula there, that's just going to be r dz dr d theta. Okay. So if we go and we look at what we have, when we were given the different surfaces there, we were given a cone and a cylinder. So for z, we know that the range for that is going to be r, or from r to 4, or you could say the range of that would be from r to 4. Based on the information that we were given. For r, the range for that, again, will be from 0 to 2. And then the range for theta will be from 0 to 2 pi. So we'll need to convert the following into cylindrical coordinates. Okay. And that's what we need to do. Okay. All right, so we got our flux here. And what you have to make sure you do, this is a very common mistake, and I did this back in vector calculus. You have to make sure you're lining the integrals up correctly with the order in which you're integrating. So you can't just have the integrals kind of laid out any way you want. You have to make sure they line up. So since we got r dz dr d theta, then that means that the range for theta, since we're going to be integrating respect to theta last, has to be on the outermost integral here, to the outermost one, which is going to be from 0 to 2 pi. So you have to make sure you're matching them up correctly. That's a mistake a lot of times also with, if you go back to my previous videos that we've done on double integrals, and we talk about Fubini's theorem, which basically, you set up the iterated integral, and regardless of what order you evaluate it in, you get the same answer when we're doing double integrals over rectangular regions. But one of the common mistakes with that theorem is that students will, again, when they go to do it in the other order, they'll forget to flip the integral around, and the limits of integration in the integrals won't match up with the order, and that's how you get the wrong answer. So you have to make sure that it matches up. And so since we're doing theta last, we're doing r, I guess you could say second to last. And so if we look at the range for those, we know that's going to be from 0 to 2, and then obviously integrating with respect to z first. In that particular case, we know what the range for those are going to be. It's going to be from r to positive 4. And then all we have to do is just substitute in. So what we're going to have is r cosine theta plus 1. Now we got to multiply that by r dz dr d theta. And this is the order in which it's being integrated. Okay. So remember that x was equal to r cosine theta, so that's where that came from. We were adding 1 to that, and then we got r dz dr d theta. So if you got lost, that's where we're at. All right. So let's deal with this triple integral here. And triple integrals aren't hard to evaluate, but I actually think setting up triple integrals is actually the hardest part of it. I don't think, well, depends on the circumstance. So we know that for the triple integrals, let me quickly go back to the sheet. We know for the triple integrals, much like for the doubles, we begin by integrating with respect to z first. So, and we work our way from the innermost integral to the outermost one. We treat the other two variables as our constants, obviously, until we get to those variables that we integrate with respect to. So let's do that. So we'll start. This would be the integral from r to 4. And again, we got r cosine of theta plus 1 multiplied by r integrated with respect to z. So since we're integrating all of this stuff with respect to z, well, you don't see any z's in here, so that means that everything here is treated as a constant. So, and evaluated from r to 4. So in that case, our outermost integral will be from 0 to 2 pi, which will integrate with respect to theta last. The innermost integral will be from 0 to 2, because now we're down to a double integral because we're treating all of that as a constant. And then what we're going to have now is r squared cosine of theta plus r, if we just distribute in the r, and then it's going to be multiplied by 4 minus r, and this time we're integrating with respect to r now, because that's the next variable that we're dealing with. Okay, so essentially what we're looking at now is the integral from 0 to 2, and it's going to be, we can expand out the expression there in just a minute, but just in case you got lost, this is where we're at after distributing in that r. Okay, now let's expand all that stuff out, and this may seem like the long way to do it, but I think that's just the way math is. Sometimes you kind of got to do things the long way, and don't necessarily like doing things the long way, but unfortunately that's just the way it is. Okay, so if we expand this out, okay, well, it looks like we'll get 4r squared, the cosine theta, we leave that alone. R squared times r is r cubed, so this would be minus r cubed. Again, cosine of theta. And then it looks like we'll have a plus 4r, and then it's going to be minus r squared, because r times r is r squared, so this will be minus r squared if we actually expand everything out. And so now the integral is going to be from 0 to 2, and we can break this up. It'll be 4r squared multiplied by cosine of theta integrated with respect to r. And then we'll have the integral from 0 to 2, and it looks like we'll have r cubed cosine of theta integrated with respect to r. We'll then add that to the integral from 0 to 2, and it's going to be 4r dr. And then we're going to subtract that from the integral from 0 to 2, r squared with respect to r. All I did there was apply the sum and difference rule for integrals. Now, these may seem like long, integrations that we need to do here. Again, all I did was apply the sum and difference rule. That's all I did there. We're essentially looking at the same thing after we expand everything out. I just broke it up into pieces, which I highly recommend doing anytime you get something long like this. Because if you just try to stick that, I guess you can kind of do it in your head, but if you just try to stick that in the integram from 0 to 2, it'll look like a jumbled mess. So that's why I broke it up, so you can see kind of how it works. Now, since we're integrating with respect to r, it's not going to be that bad. Okay, so just keep that in mind. Now let me just demonstrate how bad it's not going to be, I guess. So let's just deal with the first one. The other two will be quite easy. So let's just go through the first one. So from 0 to 2, we got 4r squared cosine of theta integrated with respect to r. So what does that mean? Well, that means that the 4 is a constant, but the cosine theta is also a constant because we're integrating with respect to r. So those can just come out front like so. And then we essentially just apply the power rule, and that'll give us r cubed over 3 evaluated from 0 to 2. And obviously this would be 4 cosine of theta multiplied by 8 over 3, because when we stick in the 2, we get 2 cubed, which is 8, so that'd be 8 over 3. Sticking in 0 just gives us 0. So we're multiplying this by 8 over 3, which we can go ahead and simplify. And remember that 4 times 8 is 32. So this becomes 32 over 3, which can't be reduced, multiplied by cosine of theta. So that is exactly what we get when we deal with the first piece. Now, again, I'm doing this the long way. When you're actually doing this in a class, you won't need to, you won't have to write that much stuff down. I'm just breaking it up for the purposes of the video. And we can even tackle maybe this next one just to kind of demonstrate how easy it is, because since we're integrating with respect to r, the other variable that is contained within is just a constant, okay, or treated as a constant. So in this case, cosine theta or cosine of theta is a constant because we're integrating with respect to r. So this becomes r to the 4th all over 4, evaluated from 0 to 2. And this will give us 2 to the 4th, 16. Divide that by 4, get 4. So that's 4 minus 0, which is 4. And we multiply that by cosine theta. And so now we go ahead and simplify everything there. And we'll integrate with respect to theta last, okay, after we simplify. So we got 32 over 3 multiplied by cosine of theta. Now these two parts here are very easy. We didn't even go through those because they're very easy. So the answer for this part would just be 4 cosine of theta, or cosine of theta times 4. And then from 0 to 2 for r dr, that's just 8. That's easy to see. And then from 0 to 2 r squared dr, that's just simply 8 over 3. So what we got is 32 multiplied by cosine theta minus cosine, I'll just write it as cosine of theta multiplied by 4. That might look a little confusing maybe. And then we'll add that to 8 minus 8 over 3. Now this is the time for you to get out your calculator, make sure your arithmetic is correct, which we'll do here. Okay, so 3 plus 8 plus 3. So we know we can reduce, so this would be 20 over 3. And our last integral will be from 0 to 2 pi, because we're integrating respect to theta. So what we'll get is 20 over 3 cosine of theta. And then it'll be minus 8 over 3 plus 8. And we'll integrate it with respect to theta, which is integrating last now. Okay. And we'll finish it up, breaking it up into small incremental steps here. So just keep doing it. Now these are even easier. So from 0 to 2 pi, and anytime you have these long expressions like this, and you could probably do it in your head, but you want to try to break it up using the sum and difference rule, just so that the jumbled mess that you see doesn't create a whole bunch of anxiety, which you can if you look at it that way. That's why I try to break it up, just to kind of show students that it's actually not as bad as it appears. I won't even write it this time. You kind of get the point. So from 0 to 2 pi, we got 20 over 3 cosine theta d theta. Again, 20 over 3 is a constant. We take the antiderivative of cosine theta, we get sine theta, positive sine theta, keep in mind. Evaluate that from 0 to 2 pi. Well, if we do that, we're going to get 0. And then if we go, let's say we did break it up a little bit, and let's say it's going to be from 0 to 2 pi. And let's say 8 over 3 integrated respect to theta. Well, 8 over 3 is a constant, integrated respect to theta. That's just going to be 8 over 3 times theta from 0 to 2 pi, which would be 16 pi over 3. And from 0 to 2 pi, remember the last one was 8 integrated respect to theta from 0 to 2 pi. Again, 8's a constant, so it's going to be 8 theta from 0 to 2 pi. And this will give us 16 pi, basically. All right. So what we got is 0 minus 16 pi over 3. And then keep in mind it's going to be plus 16 pi, not minus, plus. And this is just going to be 32 pi over 3. Hopefully you see that. 16 plus 16 is 32. And so that'll essentially be our answer. So our final answer here, when we use the divergence theorem, or Gauss's divergence theorem, our final answer here is going to be 32 pi all over 3. And that would be your answer. And that's how you do it. So it took a little bit of time to run through that one, but I wanted to provide a detailed explanation of everything that was being done. So that's why it took so long. But that is how you work through it. All right, so let me know if you got any questions. We could talk about it, and I'll see y'all next time.